All right, today we're peeling back the curtain on one of the coolest materials in modern construction, autoclaved aerated concrete. You might know them as AAC blocks. Now, it's a story all about chemistry and precision engineering, but honestly, it's a lot like industrial-scale baking. Let's get into it.
So let me ask you this. How in the world do you make concrete, that super dense, heavy stuff, light enough that it can actually float on water, but at the same time keep it strong enough to build a house with? Well, that's exactly what AAC is, and the how is what we're going to break down today.
So here's our game plan for this explainer. Think of it as our baking plan. First, we'll check out the ingredients for the perfect recipe. Then, we'll see how it's all mixed together. After that, we watch it rise, see how it gets sliced, and finish up with the final bake. It's a 5-step journey from a bunch of powder to a really powerful building block.
Okay, so first things first, the perfect recipe. And I'm not kidding when I say this is like baking, because just like any cake, the final product is only as good as the ingredients you start with, and they have to be measured out with absolute precision.
Here they are, the 5 main players. You've got your silica-rich base, that's either fly ash or sand. Then you add lime, cement, and gypsum, which basically act as the binders to hold it all together. But the real star of the show, the magic ingredient that makes this whole thing work, is that last one, aluminum powder. So, the main chunk of our mixture comes from a material that's rich in silica. A lot of the time, this is fly ash. And what's really cool is that fly ash is a waste product from coal power plants, which actually makes this whole process a bit more sustainable. You just mix it with water to make a slurry, and that forms the base, the body of the block. It's kind of like the flour in our cake recipe.
And now for that touch of magic. A really small, and I mean really carefully weighed, amount of aluminum powder gets added to the mix. This stuff is our leavening agent. You can think of it as the yeast for our concrete. Its one and only job is to kick off a wild chemical reaction that turns this dense slurry into something incredibly light and airy.
So we've got our ingredients. Now it's time for section 2, the automated mix. See, having the right components is one thing, but combining them perfectly every single time is where the real science comes in. This whole stage is all about automation and consistency.
And the level of control here is just wow. It's all automated. A dosing system weighs every ingredient down to the gram, then drops them into this massive mixing drum. They even add steam to keep the whole mixture at a perfect 40 to 42 degrees Celsius. Once it's churned into a slurry, it gets poured into these huge pre-oiled molds, getting it ready for the magic to really happen.
All right, next up is probably the most dramatic part of the whole process. Section 3, rise and shine. This is where that tiny little bit of aluminum powder gets to do its amazing work. So here's what's going on chemically. That aluminum powder reacts with calcium hydroxide and water in the mix, and it releases millions, and I mean millions, of tiny hydrogen gas bubbles. These bubbles get trapped inside the slurry as it starts to thicken, which forces the entire mixture to expand. It's literally like watching a giant loaf of bread rise in the oven.
And we're not talking a small expansion either. The mixture actually grows to twice its original volume. This process is what creates a structure of tiny, closed-off air pockets. And that's the secret sauce that gives these AAC blocks their game-changing properties. It's not just being lightweight, it's also what gives them fantastic thermal and acoustic insulation.
So after it's done rising, this huge mass sits in a temperature-controlled room for about 1 to 3 hours. At this point, it's called a green cake. Not because of the color, but green as in, not fully cured yet. This pre-curing step is vital because it lets the block harden just enough to be handled for the next very precise step.
Which of course brings us to section 4, the perfect slice. Okay, so at this point we've got a massive kind of soft block of aerated concrete. The challenge now is, how do you cut that into perfectly uniform building blocks with insane accuracy?
Well, factories usually use one of 2 main methods to do this. There's flat cake technology, where the cake is cut while it's lying down flat, and then there's tilt cake technology, where the entire mold is tilted 90 degrees so the cake is standing on its side as it moves through the cutting machines. It's the same end result, just a different way to get there. But no matter which way they do it, the cutting itself is done by an array of really taut steel wires. Think of it like a giant egg slicer. These wires pass right through the soft green cake, first horizontally to set the block's height, and then vertically to set its thickness. This is how they guarantee every single block comes out with precise, uniform dimensions.
And that brings us to the final step, section 5, trial by steam.
So the blocks have been shaped, but they're still relatively fragile. This is the stage that's going to transform them from a soft cake into a super strong building material.
The key piece of equipment here is the autoclave. And really, you can just think of it as a massive industrial-strength pressure cooker. The cut blocks get rolled inside on these little carts, the giant door gets sealed, and then they fill it with high-pressure steam. For the next 10 to 12 hours, those blocks are essentially baked under intense heat and pressure. This high-pressure steam bath kicks off a second chemical reaction, which fundamentally changes the material's crystal structure. This is what gives the blocks their final, really impressive strength and durability.
After they come out of the autoclave, it's really just a matter of the finishing touches. A machine separates any blocks that might have gotten stuck together, they're stocked up into perfect cubes, and then they're all ready to be shipped out to construction sites all over the world.
So there you have it. From a simple mix of powders to a complex chemical reaction and a final trial by steam, we get a building material that's strong, insulating, and yeah, light enough to float. It really makes you wonder, doesn't it? Now that we can engineer concrete with air, what other innovations could this kind of technology unlock?